Hi gang. Now that we've developed the thermodynamics of the Gibbs function and the Helmholtz function and understand their relationship to the second law of thermodynamics, we can begin to apply these thermodynamic functions to chemical equilibria. We'll start by looking at simple mixtures. Up to this point, we have looked at systems that consist of one component only. And so, for example, when we're looking at the Gibbs function, we can calculate changes in the Gibbs energy as a function of pressure and temperature. But again, we're only looking at one particular component. What happens if we have a mixture where we have multiple components and the compositions of those components may change? How does the Gibbs function change when we change those compositions of those components? So what we're going to do is we're going to add to our equation here a term which deals with the changes in the number of moles of particular components. So we have here in this equation dn sub I, and that will represent the number of moles of some component I, and the dependence of the Gibbs function on that component I is just simply this partial derivative, which is the derivative of g with respect to the number of moles of component I. Of course, we're going to be holding pressure and temperature and the number of moles of all the other components constant here, just as we would before. So basically, we're just adding another term to our equation, which shows how the Gibbs function does depend on the number of moles of a component I, and of course, this is going to be summed over all the components present in the mixture. So here we've just summarized what we're doing by adding this last set of terms associated with this. Now, this partial derivative of g with respect to n sub I becomes a little bit cumbersome to write every time. So we're defining a new term here, which is called the chemical potential. So this mu sub I here is called the chemical potential, but it's just simply defined as the partial derivative of the Gibbs energy with respect to the number of moles of component I. If we have a system where there's only one substance, then this becomes quite simple because the chemical potential turns out to be just equal to the Gibbs energy per mole, or the molar Gibbs energy. This should be obvious if we just realize that the total Gibbs energy of a system is equal to n times the molar Gibbs energy. Then taking the derivative of that with respect to n here is just the molar Gibbs energy. So again, this is only true for one substance, and that's actually pretty important that we understand that. So in the absence of a mixture where you have only one substance, the chemical potential is just the same thing as the molar Gibbs energy. All right, so if we have multi-component systems, and considering a situation where we have a process involving no change in temperature or pressure, so isothermal and isobaric, then changes in the Gibbs energy will be solely due to changes in the number of moles of the different substances present in the mixture. So we can, for example, think about a chemical process where we might be taking reactants, mixing them together to get products. The number of moles of the reactants will be changing, the number of moles of the products will be changing, so we're obviously interested in how the Gibbs energy changes when we change the number of moles of those. So the first equation here just very simply shows the Gibbs energy partial derivative, and that of course is nothing more than the chemical potential. And of course, if we're summing here, if we're integrating the summation, then we'll note that the integral of dni just becomes the number of moles. So in this particular circumstance, if we have a mixture, the total Gibbs energy is equal to the number of moles of a component times its chemical potential summed over all components. Again, that should make some sense to you, because if we just think about it, all this is saying, let's say we have a three-component system, then the total Gibbs energy is equal to the number of moles of component 1 times the chemical potential component 1 plus the number of moles of component 2 times the chemical potential of component 2 plus the number of moles of component 3 times the chemical potential of component 3. That's all that means. So one thing to remember, we talked about this earlier in our discussion of the Gibbs energy. For isobaric and isothermal process, we noted that the process occurs spontaneously when delta G is less than 0, and a process will proceed to minimize the total Gibbs energy of the system. So the direction in which a process proceeds is to minimize that. When we do reach a minimum, we have an equilibrium. We'll talk about that in a little bit more detail later on. But under those circumstances, the minimum G, Gibbs energy, it corresponds to a maximum entropy for the universe, as we noted its relationship to the second law of thermodynamics in the previous video. So again, as we mentioned here, that then if we have two systems that are in some kind of thermal exchange, then we will reach an equilibrium when the Gibbs energy of those two systems is the same, and that would correspond to a process when delta G would be equal to 0. And so we'll look at this in more detail later on. Alright, so let's consider a process of what's called constant pressure mixing. Let's say that we have a system which maintains a pressure of 1 bar. Okay, we have an ideal gas, and we have two chambers in which we have gas A on one side of the chamber and gas B on the other side of the chamber. And then we open up the wall between the two to allow mixing. All right, what is delta G for this process where we're mixing? Now, the thing to keep in mind is that we are maintaining a constant pressure of 1 bar throughout this process. So what would delta G be for the mixing here? The full derivation of the equation we'll find in the text, so I won't go through this right now. But so if we assume an ideal gas where the pressure is maintained at a constant value, delta G for this mixing process is given by this expression here, where the summation is over all of the different components in the mixture. And actually there is a typo here. The summation obviously should be J and not I. So we have nRT times the summation of x sub j times the natural log of x sub j, where x sub j is just the mole fraction for component j. So this involves mole fraction. So we'll ask a simple question in this process: is the mixing spontaneous? So again, going back to our previous example where we had two gases separated by a wall. We open up that wall, and we know from experience that these gases are going to mix spontaneously. But so what does the thermodynamics say about that? Does the thermodynamics indicate that it's going to mix spontaneously? Well, if we take a closer look at this equation, we'll note, of course, that mole fractions are going to be less than 1, and that means that the natural log of x sub j is going to be less than 0. When x sub j is less than 1, the natural log is going to be less than 0. And that means that delta G for this mixing is going to be less than 0. So, good thing, because we know it's going to mix spontaneously. Delta G better be less than 0 for this process of mixing spontaneously. Otherwise, we're going to have to go back to the drawing board and start over again. So this is just verifying what we already know from a thermodynamic perspective. Delta G for this mixing process will indeed be less than 0. Okay, so now let's consider a chemical process where we have reactants and products. And here we have a simple diagram which shows along the vertical axis a Gibbs energy, and along the horizontal axis what we call a reaction coordinate, where we have reactants on one side and products on the other side. Okay, so the reaction coordinate represents the progress of a reaction going from left to right from reactants to products. So we'll plot G here, the Gibbs energy, is a function of this reaction coordinate. And this is just a random drawing. It could actually be different from this. We'll note that there, in this case, is a minimum. all right, in this diagram. And that's where the chemical equilibrium would occur, where we have a minimum value of G. Remember, when the Gibbs energy is at a minimum, the entropy of the universe is at a maximum, and that's chemical equilibrium. Now, the position of that minimum is going to vary widely between from reaction to reaction. I've just drawn it here, so while it's not actually in the center, it's close to the center, but it need not be that way. We could very easily have a minimum which is very much closer to the reactant side of things, or we could have a minimum which is very much closer to the product side of things. So that's the point, is that wherever that minimum might be is where we're going to see a chemical equilibrium. The composition of the reactants and the products at that minimum correspond to the compositions at equilibrium. And of course, at that minimum, that means that delta G is going to be equal to 0. Alright, so we'll start by a simple case of gas phase equilibrium. We're going to assume that all of the gases present in the reaction behave ideally. And if we remember, going back to a previous video when we talked about the Gibbs energy and the pressure dependence of the Gibbs energy, we had a relationship like this. So this just shows the pressure dependence of the chemical potential, which is the same as the pressure dependence of the Gibbs energy. It's just that we're thinking about a situation where the number of moles is equal to 1. So we will note that to be the pressure dependence in that case, where the mu naught, let me go back here for a second, where the mu naught corresponds to the standard chemical potential, and mu sub A just represents the chemical potential at some pressure other than standard pressure. P naught, of course, here is equal to 1 bar. So there we have a chemical potential for a substance which we're calling A. Now, if we consider a reaction, simple reaction, of A plus B going to C plus D, where the lowercase letters represent the stoichiometric coefficients, we can calculate delta G at any point along the reaction coordinate by looking at the chemical potentials of the different substances at the coordinate. So we have reactants and products. Here we see the products with their chemical potentials multiplied by the appropriate stoichiometric coefficient. So we have mu sub D multiplied by coefficient D, and mu sub C multiplied by coefficient C. And we remember, of course, that delta G is equal to products minus reactants. And so we have the same thing on the reactant side with substances A and B. So delta G is just very simply equal to that, products minus reactants, as we have been using all along. Now, if we substitute the equation for chemical potential that we met on the previous slide, then we're going to substitute for mu sub D this relationship here, which is related to the pressure of D. And then, of course, we have with C, we have the same thing with the pressure of C, and then, of course, we have the same thing for A and for B. Using properties of logarithms, combining those logarithms, we come up with this simpler version of the equation here, where we'll note that we have the natural log of a quotient, where we have the pressures of each of the components raised to their stoichiometric coefficients. And we'll note that we've got products divided by reactants. All right. And then we have this here, which P naught again is 1 bar, but we add that. That's actually fairly important if we're using units other than bar in this calculation, just to make sure that we keep ourselves honest. As long as we're using pressure values in bar, then we're going to be okay. It also makes this quotient unitless, which, of course, when we're taking the natural log of something, that whatever we're taking the natural log of must be unitless. So here's our expression for delta G, and this will correspond to any place along that reaction coordinate that we looked at earlier. All right, so again, so here's the equation, and again, this is going back to the diagram that we saw earlier. It shows us, it's going to allow us to calculate the delta G value at any point on that, depending on the pressures, the relative pressures of the products and reactants. So we have this little x here. We could calculate delta G there, or on the other side we can calculate delta G there, or we can calculate delta G there. We just have to enter the pressures of the reactants and products at those particular points. Okay. We'll note on the left side, because the slope of the curve is downward, the delta G is going to be less than 0. Whereas on the right side, the slope is positive, delta G is going to be greater than 0 over on that side. So we can actually tell what the sign is going to be based on the slope of the curves here. All right, so to make our life easier, so that we understand how this is going to work, and we can apply this more readily to systems which have different numbers of reactants and products, we're going to define a reaction quotient, and you are more than likely introduced to this in general chemistry, which again is just the pressures of the products raised to the stoichiometric coefficients divided by the pressures of the reactants raised to their stoichiometric coefficient. That form should be familiar to you. Products to the coefficients divided by reactants to the coefficients. A shorthand way of writing that is using the product sign pi here, so that we don't have to write it all out. This would simply be a more general expression, which means we're going to take a product over all of the substances present, where we'll note that the nu sub I represents the coefficients, and that for products, nu sub I is greater than 0, and for reactants, nu sub I is less than 0. Again, this is a form that we've seen before. So using that, defining the reaction quotient that way allows us to write the expression for delta G in a simpler fashion. And again, remember, this will allow us to calculate delta G at any point along that reaction coordinate, provided we know the pressures of the products and reactants. All right. Now, what about equilibrium? Well, at equilibrium, at the minimum of that reaction coordinate, we'll note that delta G is equal to 0. So that simplifies it into this case, where we're indicating here that we are talking about composition at equilibrium. So we have a little EQ there for our reaction quotient to indicate that. And of course, we all know from past chemistry courses that reaction quotient is now the equilibrium constant. We call that Kp because it's in terms of pressures. The subscript P indicates that. So now at equilibrium, the pressure, the reaction quotient, product pressures divided by reactant pressures is our equilibrium constant. And of course, then making that substitution and rearranging the equation gives us this familiar expression, which you have seen and you have used before, showing delta G naught, again that's delta G at the standard 1 bar pressure, is equal to negative RT ln of K. You have used this before, I hope you remember it, but that goes back to general chemistry. Right, so that's how we would calculate equilibrium constants for gases. We're talking about pressures, and that's where pressure is, standard pressure is 1 bar. What about solutions? No doubt most of the calculations you've done in the past for equilibrium constants have been with regard to solutions. What are standard conditions there? Well, in this case, standard conditions for the solute is defined as 1 mole out. That's mole out, of course, being moles per kilogram. So when we talk about a solution which has solutes, we write delta G naught in terms of the equilibrium constant K sub m, where we're using molality instead of pressures, but the form is the same. All right. Again, you may recall for solids and solvents, standard conditions correspond to the state of the substance at 1 bar pressure, and that just very simply means that that the solids and solvents that appear in chemical reactions are already in the standard state, so we do not include them in the equilibrium constant or the reaction quotient. So we're going to ignore those in the reaction quotient. Alright, so this is going to end our discussion of the basics thermodynamics of the equilibrium constant and the reaction quotient. In our next video, we'll talk about Le Chatelier's principle and how changes in variables will cause shifts in equilibrium. So stay tuned.